Let's now take a look at another example. A plant produces oxygen by distilling air. The experimental data shows that the purity of the final product, the oxygen, may be related to the impurities in the air, measured by the pollution count in parts per million. The plot shows the experimental data as the oxygen purity, the response variable, as a function of the pollution count, the regression or explanatory variable. Clearly, the oxygen increases as the pollution count decreases. And it seems that we could fit the data by a linear model as purity equal to beta 0 plus beta 1 pollution count. But how do we calculate the regression coefficients beta 0 and beta 1? And how do we evaluate the model? The table on the left shows the experimental data used to build the plot we have just seen. The table shows the pollution count, our regression variable x, and the oxygen purity, our response variable y. The column purity shows the experimental results. Each individual observation, yi, is represented by the regression model, beta 0 plus beta 1x, plus an experimental random error, epsilon y. As we have 15 experimental observations, instead of writing 15 equations, one for each observation, we can use matrix notation for summarizing the data. The matrix of the experimental results y is equal to the matrix of the regression variables x times the matrix of the regression coefficients beta plus the matrix of the experimental errors. The first column of the X matrix is composed of number ones, since it is multiplied by beta 0, the independent coefficient of the beta matrix. The second column of the X matrix is formed of the regression variables values and is multiplied by beta 1 in the beta matrix. Our objective is to estimate the values of beta 0 and beta 1 in the beta matrix. We can calculate the beta hat matrix of the calculated coefficients as the inverse of the x transpose times x transpose times y. The notation beta hat means the estimated coefficients of the regression model obtained from the experimental data. Let's now quickly calculate it. Here we have the Y matrix from the experimental results of the oxygen purity, and here the X matrix with the numerical values of the regression variable pollution count. First, we calculate the product between the X transposed and X, and then we invert it. Now we calculate the product between X transposed and Y. Finally, we obtain the estimated coefficients beta hat by the product of the resulting inverted matrix X transpose times X by the resulting matrix X transpose times Y. The first coefficient is beta 0 and the second is beta 1. This way we have our regression model, oxygen purity equal to 96.5 minus 2.9 times pollution count. Let's now use RStudio to calculate the regression and to evaluate the model adequacy. Please download the data and the RCode files, and let's change to RStudio.